Welcome to our fifth lecture in the fifth week of our course, Analysis of a Complex Kind. Today we'll learn about consequences of Cauchy's theorem and integral formula. We'll be able to pick some fruit of our labor. Let me remind you of Cauchy's theorem for simply connected domains and also of Cauchy's integral formula that we studied during the last lectures. Cauchy's theorem says the following. Suppose D is a simply connected domain. So again, that simply means it's an open connected set, so it's in one piece, and it has no holes. And let f be an analytic function that's defined in D. Suppose gamma is a piecewise smooth closed curve in D, so gamma is some kind of curve, and it starts and ends at the same point. That's what makes it close. Then the integral over gamma, f of z dz, is equal to 0. From this theorem, we were able to conclude the Cauchy integral formula. And here is the version that we had in the very end, which also included derivatives. Suppose D is a simply connected domain bounded by a piecewise smooth curve gamma. So we have some kind of curve gamma, and it bounds the simply connected domain D. And we always orient it counterclockwise. Suppose f is analytic in a set U that contains the closure of D, so D and gamma. So we have some U that contains D together with its boundary, the curve gamma. The claim is then you can find the kth derivative of f at any point W inside D by integrating over the curve gamma the function f of z divided by z minus w to the k plus first power. Again, this is a very fascinating theorem because when we evaluate this integral, we're only taking account of values of f along the curve gamma. However, those values are able to recover for us values of f and its derivative inside the domain, so inside gamma. It's quite a remarkable theorem. The first application of the Cauchy integral formula is Cauchy's estimate, and this in turn will be very helpful in proving further results. So suppose f is analytic in an open set again, and that open set contains a ball of radius r, including its boundary. So here's this open set, we can call it U if you want to, and there is this ball of radius r that fits into U, including its boundary. So the boundary, the ball doesn't touch really the boundary of U. So here's this point Z0, and the ball has radius r. And suppose furthermore, we know that the absolute value of f is bounded above by some constant m on this boundary curve. Then Cauchy's estimate says that for all k greater than or equal to 0, the kth derivative of f at the center point z0 is bounded above by k factorial, so that's the same k as the derivative that we took here, times m, the constant that bounds f on the circle of radius r, divided by r to the kth power. And the proof is actually quite simple and simply uses the Cauchy integral formula, which I wrote down for you up here so you would remember what it looks like. So what we're going to do for the proof, we're going to plug in z0 for this point w right here. And therefore find that fk of z0 is k factorial over 2 pi I times the integral over gamma f of z divided by z minus z0 to the k plus first power dz. So that's what we have right here, and there are absolute value signs, so we put those absolute value signs there as well. The curve gamma in our case is the circle of radius r, oriented counterclockwise, so I just wrote z minus z0 equals r right there. But now we remember that we had some sort of triangle inequality for integrals. In other words, we can pull the absolute value signs inside at the expense of an inequality sign. So the absolute value of this integral is bounded above by the integral over the absolute value of f of z divided by the absolute value of z minus z0 to the k plus first power, absolute value of dz. And remember what the absolute value of dz means? It just means that when we plug in the parametrization, we take the absolute value of the derivative, gamma prime of t, dt. But we don't even have to plug in any kind of parametrization. What we observe next is that along the entire curve gamma, no matter what t value I plug in for my parametrization, this term z minus z0 is always equal to r in absolute value, because my parametrization will put these z values all the way around z0 on the circle of radius r, but the absolute value, the distance from z0, will always remain r. Therefore, from this integral, I can pull an r to the k plus first power out of the denominator. See that right here? It's no longer in the integral. I keep the 2 pi that I had over here and the k factorial right here. Furthermore, in the numerator, I know that f of z by my assumption is bounded above by this constant m on the curve gamma. And that's where this m comes from right there. And what I'm left with after doing all that would be k factorial divided by 2 pi times m, that's my estimate for f, over r to the k plus 1, times the integral over z minus z0 equals r, absolute value of dz. I've pulled the rest out of the integral. However, the integral that I look at right here, that's the length of the curve gamma. The curve gamma is the circle of radius r centered at z0. The length of that's 2 pi r, and that's what you see right here. Now we can simplify. Let me clear the screen. And we can simplify that 2 pi's cancel out, one of the r's cancels out, and I'm left with k factorial times m divided by r to the k. And that's what we wanted to prove. So let's see how we can apply Cauchy's estimate to prove some amazing facts. One of them is Leovolts Theorem. So here I'm just reminding you of the estimate we just proved. We proved that the kth derivative of f at z0 is bounded above by k factorial times m over r to the k, provided that we had this circle of radius r centered at z0 that fits inside the domain in which f is analytic, and that f of z is bounded above by m for z minus z0 equals r on the boundary of that circle. The consequence is Leovolts theorem. Suppose f is an analytic function in the entire complex plane. We call those entire functions because it's analytic not just in a subset but in the entire complex plane. If this function f is bounded, then it must be constant. Now this is a totally amazing theorem. It says that there are no non-constant analytic functions that are analytic in the entire complex plane. As soon as you're analytic in the entire complex plane, you can't be bounded. That is very different from what we know to be true on the real line. For example, we have the function sine of x on the real line. It's very bounded. It just goes up and down, but it never gets bigger than 1 and never gets smaller than -1. So it's very much bounded on the real line. Because this function sine of z extends to the complex plane as an analytic function, we know that extension can no longer be bounded. That means there must be some direction in which the sine function goes off to infinity in absolute value. So that is quite remarkable. Let's look at the proof of Leovolts theorem. So suppose that the function f is bounded, which would mean that the absolute value of f of z is bounded above by some constant m for all z and c. Pick a z0, any point z0 in the complex plane. Since f is analytic in the entire complex plane, we can put any ball of any radius r around that point z0, and that ball will be one of those balls that is allowable to apply Cauchy's estimate, because the function f is analytic in the entire complex plane. So no matter how large a ball I choose, it'll always fit into the domain where f is analytic. So now we can apply Cauchy's estimate to f in that ball. And we're going to apply it with k equals 1. When k is equal to 1, we get the first derivative of f at z0 is bounded above by 1 factorial times m over r to the first power. In other words, we get f prime of z0 is bounded above by m over r. But this is true for any r greater than 0. So we can choose a really, really large value for r, as large as we want to. So we can, in fact, let r go to infinity. And if we do that, this number on the right-hand side here gets smaller and smaller and smaller because m is a fixed number. If we divide this fixed number m by a really, really large number, this number will go to 0. In other words, the derivative of f at z0 has to be equal to 0 because it is smaller in absolute value than any number I can come up with. Since z0 was an arbitrary point, we can repeat this at any other point in the complex plane and find that the derivative of f is equal to 0 everywhere. But an analytic function whose derivative is equal to 0 is a constant function. So if I have a function that is analytic in the entire complex plane and bounded, then it must be constant. Let's look at an example. Suppose f is an entire function, so we could write it as u plus iv, where u is the real part, v is the imaginary part. And suppose that the real part is less than or equal to 0 for all z and c. That already implies that f must be a constant function. So not even the real part can be negative or non-positive for all z in the complex plane. An entire function whose real part is non-positive must be constant. How do you prove that? The idea is to look at the function e to the f of z instead. And we're going to show this function g, which is e to the f of z, is constant, and then conclude that f is also constant. So let's look at this function g. First of all, we know this function g is also an entire function because f is an entire function. And now let's find its absolute value. But the absolute value of e to the f of z is e to the real part of f of z, because we proved in general that the absolute value of e to the z is equal to e to the real part of z, or e to the x. But the real part of f of z, that's u of z, so the absolute value of g of z is e to the u of z. And we assumed that u of z is less than or equal to 0 for all z. So this exponent here is less than or equal to 0. It's a real number that's negative or non-positive. And therefore, that's less than or equal to e to the 0, which is 1. So now we know this function g is bounded. It's an entire and bounded function, and therefore by Leovolts theorem, g must be constant. From there, we can conclude that f is constant by looking at the derivative of g. So let's do that. What is the derivative of g? We'll look at this equation right here. G prime of z is equal to, now we need to find the derivative of e to the f of z. We need to apply the chain rule. The derivative is e to the f of z times f prime of z. And we know that g is a constant function, so g prime is equal to 0. How can the right-hand side be equal to 0? So e to the something is never equal to 0. In other words, it must be the case that f prime of z is equal to 0 for all z. But f is an analytic function now whose derivative is equal to 0. That means f is constant, and that's what we wanted to show. Another consequence of Leovolts theorem, which in turn was a consequence of the Cauchy integral formula, is a proof of the fundamental theorem of algebra. There are many proofs out there for the fundamental theorem of algebra, but this one is an amazing proof because it comes from complex analysis. Any polynomial p of z of the form a0 plus a1z all the way through anz to the n, where all these coefficients a0, a1 through an are complex numbers, n is at least 1, and the nth coefficient is non-zero. Any such polynomial, we claim, has a 0 in C. So there exists a point z0 such that when I plug that into p, I get 0. So no matter what polynomial I give you, for example, p of z is equal to 14z to the 5th minus 3z squared plus iz minus 14 minus 2i. So this is a polynomial, and in this case we have n is equal to 5 and an is equal to 14. So that's non-zero, and so the assumptions are satisfied. The theorem says there exists a point z0, I can plug in a certain z0 that makes the right-hand side equal to 0. Of course, I have no idea what that point is. This theorem doesn't show me how to find that point. It just guarantees the existence of such a point. Let's look at the proof. This is a proof by contradiction. So suppose to the contrary that you can find one polynomial p as in the theorem that has no zero. So no matter what you plug in there, you're not going to get 0. Then you can look at 1 over p of c. And since p was an entire function and is never equal to 0, we're never dividing by 0. Therefore, this new function f, which is 1 over p, is also an entire function. Our goal is to apply Leovolts theorem to f. So we want to show that f is a bounded entire function, thereby using Leovolts theorem making f a constant function, and then we can conclude that p also must be constant. So how do we do that? We want to show that f of z is bounded. So we want to show f of z is bounded above by some constant m. We can do that by showing in turn that p of z, which is 1 over f of z, is greater than or equal to some constant, bounded away from 0. If that is the case, then f of z, which is 1 over p of z, is bounded above. So that's our goal now. Well, here's p of z again, and I rewrote it a little bit. I just factored out a z to the n from p of z. So here's my an. an minus 1 only had a z to the n minus 1, so I factored out too many z's, so I need to divide by z here, all the way through a0 divided by z to the n. Now let's put absolute values on there. So the absolute value of p of z is the absolute value of z to the n times the absolute value of what's in parentheses. And my claim is that is greater than or equal to the absolute value of z to the n times, I put absolute values around the individual terms and negative signs in between them. And what I'm using here is the reverse triangle inequality, which you may or may not remember. So let me remind you. It is true in general that the absolute value of the sum of two complex numbers a plus b is greater than or equal to the absolute value of a minus the absolute value of b. We also had the regular triangle inequality, which said that a plus b is less than or equal to the absolute value of a plus the absolute value of b. But this one up here is the reverse triangle inequality, and that's the one we're using over here. We're using a generalized version with more than two terms, but it's the same idea. So the absolute value of an plus an minus 1 over z and so forth is greater than or equal to the absolute value of the first term minus the absolute value of the second term minus the absolute value of the third term and so forth. But now the great thing is we're going to let z go to infinity. So as z gets larger and larger and larger, this whole remainder goes to 0 because we're dividing by z. So when you plug in a really large value for z, the coefficients are fixed, and so these terms get smaller and smaller and smaller. An is some fixed number as well, and then we're multiplying that fixed number with this larger and larger and larger and larger term. So altogether that goes to infinity as z goes to infinity. So p of z just gets larger and larger and larger, and therefore f of z goes to 0 as z goes to infinity. Well, f of z going to 0 as z goes to infinity means it's going to be rather small as long as z is large enough. So for example, you can find a radius r such that outside of the ball of radius r centered at 0, f of z is less than or equal to 1 because it has to go to 0. So I already know that f of z is less than or equal to 1 out there. But inside this closed disk of radius r, f is a continuous function and therefore cannot go off to infinity. So f is bounded by some constant m. Inside here, altogether it is bounded by whichever is bigger, little m or 1. Therefore, f is bounded in C. But by Leovolts theorem, that implies that f is a constant function. But if f is a constant function, then 1 over f, which is p, must also be a constant function. And that's a contradiction, because we said p is a polynomial with an being non-zero and n is at least 1. So that's not a constant function. So we were able to prove the fundamental theorem of algebra using basically the Cauchy integral formula. A consequence is that you can factor polynomials in C. Any polynomial of the form that we just saw before, so P of z was a0 plus a1z and so forth through a and z to the n, can be rewritten as a product z minus z1 times z minus z2 all the way through z minus zn, where these numbers z1, z2 through zn are the zeros of P. So those points, when you plug them in, P is equal to 0. They're not necessarily distinct, but there's n of them right here. Here's an example. The polynomial P of x equals x squared plus 1 has no zeros in R. You can graph that. X squared plus 1 is just a parabola shifted up by 1. It never crosses the x-axis. No matter what x I plug in there, it's never going to be equal to 0. So I cannot factor that, because if I could factor that, then it would have some zeros. So I cannot factor this in R. But in C, if I allow complex numbers to be plugged in, I can factor z squared plus 1. It has the two zeros I and minus I, because when I plug in I for z, I squared is -1 plus 1 is equal to 0, and similarly minus I. And so in C, I can factor this as z minus I times z plus I. You can try this out. If you multiply through, you get z squared plus iz minus iz minus I squared. What is that? That is z squared. Iz and minus iz cancel out. I squared is -1 with a minus sign here. Gives me a plus 1. That's the polynomial I started with. Another consequence of the Cauchy integral formula is the following result. We'll skip the proof here. It's called the maximum principle. Suppose f is an analytic function in a domain D, and suppose there exists a point somewhere in D, C0, such that the absolute value of f of z is largest at that point C0. Then f must be constant. So f cannot have a maximum value in absolute value anywhere in a domain where it is analytic. There's always a direction where it's going to get bigger. This is very non-true in R. Right? You can draw lots of functions that have maxima. There you go. So this function has a maximum right here and a maximum right there. Or the sine function has lots of local maxima value. There and there and there. But if you look at the sine function as you extend it to the complex plane, if you make this three-dimensional, and look at the absolute value of sine z, on the real axis, that's where the absolute value would, go like this. But there must be a direction such that f gets actually bigger. So here it gets smaller, but there must be another direction in which it gets bigger. And that is indeed the case. Here's a consequence. Suppose D is a bounded domain and f is a function that's continuous in D including its boundary and analytic in D. Then the absolute value of f reaches its maximum on the boundary. So here's this D, and f is analytic in D, but still continuous on the boundary. We know since D is a bounded domain and f is continuous on the boundary and the domain itself, that f must have a maximum somewhere. It can't occur on the inside, so it has to occur on the boundary. Let's look at an example. Let's look at the function f of z equals z squared minus 2z, and suppose we wanted to know what is the maximum of the absolute value of f on this square, the square Q, consisting of all x plus iy, where x and y are between 0 and 1. So I drew this square right there. Well, since this function z squared minus 2z is analytic inside Q and still continuous on the boundary, it's in fact an entire function, we know that the maximum of absolute value of f must occur on the boundary, so on these red curves. And so all we have to look at are these red curves. So let's look at them. On gamma 1, the first curve down here, the imaginary part is 0. So y is equal to 0. And the real part is between 0 and 1. So x is between 0 and 1. Y is equal to 0. So what is f of z? F of z is simply f of x because y is equal to 0. And f of x is x squared minus 2x. The absolute value of that is the absolute value of x times x minus 2. That is actually 2 minus x times x because x is between 0 and 1 in absolute value. What does that function look like? 2 minus x times x is actually an upside down parabola that intersects the x-axis at 2 and 0, and so its maximum must be at 1. We're only interested in this portion anyway. And so the maximum is right there, and the maximum occurs at x equals 1, and f of 1 is equal to 1. So we know that on gamma 1, f of z is bounded at f by 1. We do the same thing for gamma 2. Gamma 2 is the boundary here on the right. On gamma 2, the imaginary part is between 0 and 1, and the real part is fixed at 1. So f of z is equal to f of 1 plus iy. So we plug in 1 plus iy for z. We get 1 plus iy squared minus 2 times 1 plus iy. But 1 plus iy squared is 1 plus 2iy plus iy squared. But iy squared is minus y squared. And then we get a minus 2 iy from the second term. And that's what you see down here. You notice the 2 iy's cancel each other out. And we can combine the 1 and the 2 into a negative 1 minus y squared. The absolute value is y squared plus 1. The maximum of that occurs obviously when y is the largest possible, which is y equals 1. So the maximum occurs at y equals 1, and we have f of z is bounded above by f of 1 plus I, which is equal to 1 squared plus 1, or 2 on gamma 2. You do the same thing for gamma 3 and gamma 4. There you observe that f of z is bounded above by f of I. F of I is equal to I squared, which is negative 1, minus 2i. The absolute value of I squared minus 2i is actually square root of 5. And so on gamma 3 and gamma 4, f is bounded above by square root of 5. That's the largest of all the values we found in the boundaries, so this must be the maximum of f. So we see that f of z is bounded above by f of I, which is square root of 5 on all of q. Next week, we'll be studying series representations of analytic functions. We're coming up on our last week of our course, which is week 6.